So this is concrete path. Here we have the that problems for your compaction. Problems for compaction. Let's take that. So we have that embankment construction. We have to construct the embankment. Embankment we have to construct. Embankment construction is there. Okay. And I want to have that what you call as I want to attain the density that density is attained by field compaction. So density of that soil is attained by field compaction test, field compaction test, and that is actually calculated by the sand bar method, sand jar method, sand jar method. So your density calculation is based on sand jar method. That is a field method for calculation of density. Let's say that the material, the soil density is calculated by the sand jar method. For that, let's have the data. We would say your test pit of the, let's say that there was some sand or there was some soil. You have compacted that sand. You want to now check for this particular embankment. You have made new embankment is there, and this soil is newly compacted soil. And I want to say what is the density of that particular soil. For that, I had to excavate a little bit of area. Let's say that this is your area excavated. Area excavated. It's similar to that of one of the method for density calculations. We have that sand replacement method. We have talked about that. It's similar to that sand jar method. So we are excavating some area here, area of the site. So from that we can take some weight of the soil outside, weight of the soil taken out, and we need to say what is the volume of the soil taken out, and from that we can say weight of the soil by volume of the soil is equals to gamma of the soil. So that we need to calculate. That we need to calculate. So let's have the finally let's talk about this problem. What is the problem all about? So it says that we have taken weight of the soil taken out. Weight of the soil taken out is equals to how much? That is weight of the soil excavated. We can write weight of the soil excavated. That is 2883 grams. Okay, 2883 grams. Now we are going to replace this soil by, now because there is excavated area, there is no soil in that what in that particular area of the particular part of that field. So here we have this empty area. So we need to fill it with the sand now, based on the method that is sand jar method. Let's say that we have filled now it with the sand. Let's say that this is sand now, and I would say weight of the sand uh, for filling that area, excavated area, for filling completely that excavated area, for filling excavated area. Weight of the sand for filling excavated area equals to 2356 grams, 2356 grams. And we already know what is the density of that sand, because this is also predetermined that what is the density of the sand. Density of that sand we already know based on this method. Density of the sand is 1.52 grams per cc. So now we need to say what is the density of the actual soil in the field, in the actual construction where the embankment is constructed. At that side we have compacted that soil. What is the density of that compacted soil? So let's calculate the density of the soil. So that can be calculated as what is the soil weight taken out divided by volume of the pit. What is the volume of the pit? So can you calculate what is the volume actually from this data? Can you calculate what is the volume that we have excavated? So that's actually your 2356 grams weight of the sand divided by density of the sand. Can you get that from this? So your volume of the pit is actually how much? 1550 centimeter cube. And we can say the density of that compacted embankment, we can write compacted embankment, that is weight of the soil taken out, that is 2883 grams divided by your volume of the pit, 1550 grams, 1550 centimeter cube. So that's your 1.86 grams per cc. And let's say that I want to calculate gamma dry. Let's say that I want to calculate gamma dry. So I want to calculate gamma dry of the soil in the newly compacted embankment. In the newly constructed embankment, the compacted soil there. So for that, we need to calculate gamma dry. If the water content was how much? 16%. If the moisture content in the soil is 16%, now I can say what is the density, dry density of that soil in the compacted zone. That's 1.86 divided by 1.16. Okay, let's take one more. Let's take one more problem. Let's take one more problem. We can have, let's say that we have a rock content in the fill. Raw content in the fill. Let's say that there is some general soil. We can call it as a fill. Fill material is there, and it's having some raw content, and there is some soil content also. So let's say that raw content is equals to 80%. 80% by dry weight. By dry weight. And that means there is some soil also. So soil content is actually 20%. Soil content is 20%. 20%. Okay. And void ratio for your rocks is that minimum void ratio for rocks, rock fraction is 0.73. Minimum void ratio 0.73. And we need to say what is the maximum dry density to which soil fraction can be, yeah, what is the gamma dry maximum to which fill can be compacted. So we need to calculate what is the gamma dry maximum that can be achieved for your to which we can write to which your fill can be compacted, to which fill can be compacted. So your fill is actually sum of rocks plus soil. So your void ratio for the what you call as your void ratio for the rock part is 0.73. From that we can get from that we can get what is the density. At the minimum content we can get maximum density for rock fraction. We can get maximum density for rock fraction. So we need to say what is the data given for the soil. We need to see whether there's any data given for the soil. So let's see that is there any data given for soil. So then we have to say what is the net effect of those two for final density of the fill. Let's see that whether any data is given for your soil also. So one more statement might be there. So it's saying that gamma max for your clay fraction or for your soil fraction, gamma max for your soil fraction, it is actually equals to 1.63 grams per cc. This is in the dry condition. So gamma dry max for your soil fraction is 1.63 grams per cc. Your G for the rock solids, your specific gravity for the rock solids is 2.56. 2.56. And we need to calculate now what is the maximum density to which fill can be compacted. How can you solve that? How can you solve that? Let's say that we don't have any data given to us. Let's say that we have 100 grams of, let's say that we have 100 grams of total fill, 100 grams of fill. That means we're having 80 grams of rock would be there, and we are having 20 grams of soil. 20 grams of soil. So we have selected that we have this much amount of what you call as 100 grams of dry fill, 100 grams that is dry in the dry state. So we need to say what is the dry max, what is the maximum dry density, what is the maximum what you can call density of the fill. So I would say let there is some dry weight of the fill divided by there is some weight total dry volume of the sample. So that's your gamma dry maximum. So we don't have any data given to us. We would say let's assume that we have 100 grams of the total dry sample of the fill, such that 80% of that is actually raw content and 20% is because of the soil content. Now I would say that your rocks are 80 grams. Your rocks are 80 grams. Can you get the volume for that particular volume of for that particular 80 grams? Can you get what is the volume occupied by 80 grams? What is the volume occupied by 80 grams? So I would say I would say that your density can now be solved. Your density of the fill can be solved now your 100 grams is ore. 100 grams is ore. Now I want to say what is the total dry volume of the soil, dry volume of the pit. What you can call it is a fill. So that's because of volume of what was your rock and plus volume of soil. Now we need to solve for the volume of rock and volume of soil. For that, your gamma for individual values is to be taken. So gamma is to be used there. Okay. So volume of the rock can be calculated from the so we have the equation that gamma equals to weight by volume. If I know we have 80 grams of rock and we need to calculate what is the volume of the rocks, I should know what is the gamma of the rocks. For that, I can write your dry density of the grams rock is actually G gamma W1 plus E. Your data for the rock is given that your G for the rock is 2.56. Your G for the rock is 2.56. So we can write 2.56 into unit weight of water. We can write in terms of grams divided by 1 plus E. So for your gamma to be maximum, because the problem is saying that we need to get maximum density. For maximum density, it's because of if density of the what you can call rock is more, and if density of that soil is also more, so such that final density is more. So for that, gamma dry has to be maximum. At that time, your void ratio for the rock should be minimum. A minimum should be there, 0.73. So G gamma W by 1 plus E minimum. So this is your density for your rock, and that's actually equals to 80 grams divided by volume of the rock. So get the volume of rock. Get the volume of rock. Get the volume of rock. Let me calculate that. I would say we have this 2.56 divided by 1.73. That's 1.47. That is 1.4798. So finally, I had to divide that 80 by that answer. So this is 54.0. So your volume is 54.0625. Is that is this the volume? Is this the volume? 80 grams by that 1 point some value. Let's say that we got this value. Let's say that we got this volume. We don't know exactly. Let's say that we got this value 54.0625. And what is the volume of the soil? Soil fraction. So your volume of the soil fraction can be said what is the weight of the soil fraction divided by what is the gamma of the soil. So that is actually your gamma of the soil was given to be maximum. It was given to you. Your gamma for the soil fraction is 1.63, and your 20 grams of the soil was there. 20 grams of the soil. So that is 20 gram by 1.63. Yeah. So that's 20 by 1.63. How much is that? 12.2699 centimeter cube. So that is the volume of the soil. So if I substitute those values here, I would say 100 grams is there, and divided by 12.2699 plus what was the one more value we have? 54.0625. So let me check that. What is the total value coming to be equals to? So your overall value is coming out to be 1.5076 grams per cc. It's the maximum dry density of that fill material because of that, because of rock material and because of what you can call soil material, soil fraction. 80% rock, 20% soil fraction. 1.5076. So that was all about that problem. Let's take one more. Let's take one more problem. Let's take one more. Let's say that. So we want to construct embankment. We want embankment construction. Okay, embankment construction by compacting the soil, from borrow pit, And what is the soil? That is what is the natural condition for your a bore pit soil. What is the soil conditions at that natural condition? So natural condition is that we have water content of 9% in the soil, and your bulk density of the soil is 1.78 grams per cc. And we need to say, what about the embankment we have to design? There should be some specifications for your embankment. So for the embankment, compacted soil should be soil should be compacted at optimum moisture content of what you can call 22.5%, and maximum dry density at that moisture content should be 1.66 grams per cc. Okay. Now we need to calculate now, find the quantity of soil to be excavated from borrow pit. Okay. And one more data we need to say, we need to solve for, find the quantity of water to be added now. Extra water, we can say. This is the extra water we had to add. What is the extra water we have to add? That is the quantity of water to be added in the soil, such that your water content is that we are having this 22.5%, and initially we have 9% water content. Okay. And we would say we can calculate the quantity of soil from the borrow pit, but for how much? What is the need? What is the total need in the embankment? We have to say for how much. So I would say for 1,000. Is that 1,000? For 100 meter cube of soil, finished product. That means that is already compacted. At that particular condition. At this condition, it is specified that it's finished at this condition. So we have to make sure that our condition specifies at a water content of 22.5% and gamma dry maximum of 1.66. At that finished condition, I have to make 100 meter cube of soil in the embankment. So for that, calculate the quantity of soil to be excavated from the borrow pit. So let's go for the solution. So I would say for 100 meter cube of soil at a gamma dry maximum equals to 1.66 grams per cc. That's actually equals to weight of the dry soil. That's actually weight of the solids divided by volume of dry soil. Now I would say, what is the volume of the dry soils in the embankment? So this is actually for the embankment. We can write. I am writing for the embankment. So gamma dry is given to me 1.66, and that's actually dry soil weight divided by dry volume soil. So dry volume soil is actually 100 meter cube, and divided by weight of the solids. So I can get the weight of solids required. Weight of solids is actually 100 meter cube into 1660 kgs per meter cube. So that's coming to be equals to 166 tons. 166 tons, that's actually 166 into 10 power 3 kgs. Okay, I got this much amount of weight of solids required, and for this much amount of weight of solids required, I had to say how much soil I had to excavate from the borrow pit. For this much amount of weight of solids, I had to say what is the total volume of soil. Is it in terms of volume? I had to solve for the quantity of soil. So I can either solve in terms of volume, or I can also solve in terms of weight of the soil required. So let's go for the what you can say. Let me check. Let's go for the in terms of meter cube. Let's have the quantity of soil in terms of meter cube. So is there any data for your borrow pit? So your borrow pit is saying I have the density, bulk density. Let's say that this is for a borrow pit. This is for the borrow pit. Your bulk density is 1.78 grams per cc. That is actually equals to weight of the soil divided by volume of the soil. And I had to solve for the volume of soil required. That is the problem we had to get. We had to solve for this one. Volume of the soil required for 100 meter cube in the embankment. For 100 meter cube of soil in the embankment, I have to say what is the soil from the borrow pit. This is the volume of soil in the borrow pit. How much volume of soil in the borrow pit I have to excavate for 100 meter cube of soil in the embankment. So this 100 meter cube of embankment means that I have a weight of solids equals to 166 tons. I have to get the 166 tons from the borrow pit. I had to I had to acquire 166 tons from the embankment, sorry, from the borrow pit. So from that we can say what is the total volume of the soil required? So we can solve that. So I would say what is the weight of the soil? That is actually weight of the solids into 1 plus water content in the borrow pit divided with the volume of the soil. So we can get the volume of the soil now. So we can solve for the volume of the soil. We know what is the water content? What is the water content here in the borrow pit? 9%. 9%. 1 plus 0.09 divided by volume of the soil is equals to how much? 1.78 grams per cc. 1.78 grams per cc. So you can get the value of volume of the soil required. So volume of the soil required from the borrow pit is actually equals to meter cube equals to 101.65 meter cube. And I needed only how much? How much I needed for embankment? 100. So for 100 meter cube of embankment, I need 101.65 meter cube of soil from the borrow pit. Okay, that's the job we had to calculate for. And one more data we need to solve for: quantity of water to be quantity of water to be added. Quantity of water to be added. So I would say quantity of water to be added is actually equals to quantity of water to be added is equals to, because I would say weight of the solid is fixed. If your water content initially was W1 and water content in W2 is there W2, so that's actually weight of water in the initial condition divided by weight of solids, and this is weight of water in the second condition divided by weight of solids. If the weight of the solids is actually same, I would say what is the quantity of water? Delta W. W. That's actually water content 1 minus water content 2 mod of that into weight of solids. So for the addition, I would say W2 minus W1, because we had add. That means in the second condition, there should be more water. So W2 minus W1 into weight of solids. So W2 minus W1. So W2 minus W1, we can have the two values of W. One is your optimum moisture content, 22.5 minus 9. 22.5 minus 9. 22.5 minus 9 into weight of solids. This was your 166 tons. 166 tons. So we can solve for that. Quantity of water is 22.41 tons, and that can be solved as this is weight, and we can solve it as gamma W into volume of the water, additional water. So this is the volume of the water. That's extra water we had to provide in terms of volume. That is some meter cubes. Some meter cube is there, 22.41 meter cube. Either in terms of tons we are solve, or in terms of meter cubes. Okay, that is the solution for that. Let's go for the final one. Let's go for the final one. That's your final problem. Final one. So we have to construct an embankment. So total volume of the soil in the embankment for embankment construction. Embankment construction is equals to 64000 meter cube. Let's say that there is some construction of that embankment, and total volume required in the compacted state is that this much amount of volume I had to compact. That should be final volume of 64000 meter cube. Okay, and there should be some specifications. Yeah, lab, we have performed the test for your soil. For your soil, we have performed the test in the lab. Optimum moisture content was given, calculated to be 19.5. Gamma dry maximum 1.72 grams per cc. And what about the borrow pit? What about the borrow pit? What about the borrow pit? Borrow pit is that we have gamma bulk. Yeah, we have moisture content. We have moisture content of 14%. Void ratio 0.63. Specific gravity of solids 2.68. Now we need to say number of trucks required. What is the number of trips, or number of trucks required, or number of trips we can say. If one truck capacity is that it can transport how much amount of soil, 5.5 ton. So this is the one truck capacity. One truck capacity is that this much amount of weight of soil can be carried in one what you call it, one trip we can say. So we need to calculate number of trips or number of trucks we can have, and we also need to solve for quantity of water, quantity of water to be added, quantity of water to be added in the borrow pit soil, in the borrow pit soil uh, that is excavated. So that is excavated initially. So we had to transfer it to what you can call it as, we had to transfer this soil, borrow pit soil, to the embankment side, to the embankment side. Okay. Then after that we are going to add water. Now water is added. That extra water we have to calculate such that after that there is compaction. After that, after addition of water, after water addition, now we are going to compact the soil at that particular W2 water content. That is actually optimum moisture content. So initially the water content was given. That can be calculated from SEVAG. So from that we can say what is the initial water content. So after adding now water, our water content becomes W2. That is actually optimum moisture content. Now we are compacting the soil at that condition. So we need to say what is the extra water we had to add, and what is the number of trucks we had to what is the number of trips for your soil to be carried. So let's say that from the data of embankment, I would say what is the volume of solids, or we can say what is the weight of solids required. If there is total volume of, if I say that your gamma dry maximum in the embankment is actually 1.72, what was that? 1.72, yeah, 1.72 grams. This is 1.72 grams. So 1.72 grams per cc. So this is actually equals to weight of the solids, that is actually dry weight of the soil, divided by dry volume of the soil. Dry volume of the soil. So I would say your dry volume of the soil is actually total volume of the soil, 64000 meter cube. So we can say what is the weight of the solids required. What is the weight of the solids required? So we can solve for the weight of the solids. Weight of the solids coming out to be equals to, weight of the solids coming out to be equals to how much? So let's say that we got in terms of kgs, we are calculating 11008 10 to the power 7 kgs. That is also, we can say that's 11.008 10 to the power 4 tons. This much amount of tons, or in terms of kgs, we have this weight of the solids required to be taken from the water pit. So for this amount of weight of solids, I would say what is the total volume of the soil I had to excavate. Yeah. Now I would say whether I would calculate in terms of volume of the borrow pit, or I had to calculate in terms of weight of the soil of the borrow pit. So I have two options now. I can solve in terms of volume of the borrow pit required, or weight of the soil of borrow pit required. But if I see that the data, the question is asking about number of trucks, number of trips. If the one truck is capacity is in terms of ton, so in terms of weight is given, the data is in terms of weight. So I can calculate the date, all the soil from the borrow pit required is actually calculated in terms of weight of the soil. We have to solve for the weight of the soil required from the borrow pit. So I would solve in this way. Weight of the soil from the borrow pit, and that I would say weight of the soil in the borrow pit is actually that's actually equals to weight of the solids into 1 plus water content in the borrow pit. I can solve it in this way. And I have the equation for your weight water content for your borrow pit. Since your water content in the borrow pit is not given, yeah, it is given actually. So your water content in the borrow pit is given, so I can finally substitute that value of 0.04, 0.14. 1 plus 0.14 times weight of the solids. Your weight of the solid is required is actually 11.008, 11.008, 10 to the power 4 tons. So I can get the weight of the soil required from the borrow pit. So that's some value. Let's say that this is the total value. And I would say what is the number of trips required? Number of trips. Number of trips is equals to total weight of the soil divided by one truck capacity, 5.5. So I can say number of trips is equals to weight of the soil in the borrow pit divided by capacity of one truck. Capacity of one truck. So we have to divide this one. That is 5.5 kilonewton. Is it tons or newtons? Kilonewtons. That is 5.5 tons. 5.5 tons. 5.5 tons. 5.5 tons. So we can solve for that, and you can get number of trips for your carrying of that particular amount of soil. That is coming out to be 22817 trips. 22,817 trips. This much amount of trips of that one truck we have to carry. We should have such that your soil is carried finally. Okay. Now, second part of the problem is that we need to calculate for the quantity of water to be added in the borrow pit soil such that your final moisture content is how much? Final moisture content is 19.5%. Your final volume content. So I would say, what is the water to be added? Delta water is to be added. That is water content 2 minus water content 1 into that weight of the solids. So final water content is actually optimum moisture content. That is 19.5%. So we can write 0.195 minus initial water content is 12% into weight of the solids. Weight of the solids. Weight of the solids. So this is the total weight of the water to be added. Weight of the water to be added. So 6054.4 ton. This much amount of tons of water I have to add. I have to add this much amount of tons of water. So that's all about that compaction of the soil. Thank you for watching our series for your geotechnical engineering. Thank you for watching.